Imagine, if you will, looking up at the night sky at the countless stars and distant galaxies, and realizing that everything you can see, everything astronomers have ever detected from the closest moon to the most remote quasar, might just be a tiny speck within an infinitely larger cosmic ocean. Picture our entire observable universe, all its 13.8 billion light-years of visible expanse, as a single, gently shimmering bubble. And then imagine that this bubble is not alone, but is floating alongside countless other bubbles, each a universe in its own right, perhaps, with its own unique laws of physics, its own distinct history, maybe even its own forms of existence, or perhaps none at all. This breathtaking vision of a multiverse, a collection of universes, is what we're going to drift through tonight. We won't be diving into complex equations or rigorous proofs, because for many of these ideas, such things are still far beyond our grasp. Instead, we'll gently explore some of the most mind-expanding theories that suggest our universe is not the only one. The aim is to let these vast, almost incomprehensible concepts wash over you, sparking a sense of wonder and cosmic perspective as you ease towards sleep. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And as we journey through these myriad cosmic possibilities, if a particular multiverse theory resonates with you or sparks a curious thought, feel free to share it in the comments below before you drift off. It's always intriguing to ponder which cosmic narratives capture our imagination. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. Our first cluster of multiverse theories emerges from one of the leading ideas about the very early moments of our own universe: cosmic inflation. Inflation theory proposes that in the tiniest fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid, exponential expansion, ballooning from subatomic size to something astronomically vast almost instantaneously. This inflationary period smoothed out the universe, explaining why it appears so uniform and flat on large scales today. Now imagine that this inflationary process, once started, doesn't entirely stop everywhere at the same time. This is the idea behind eternal inflation. Picture a vast ocean of inflating space-time. In some regions of this ocean, the inflation might locally slow down and stop, forming a pocket, a bubble, where energy converts into matter and radiation, leading to a Big Bang-like event and the birth of a universe like ours. However, the ocean of space-time between these bubbles continues to inflate at an astonishing rate, creating ever more room for new bubbles to form. So you have an endless, self-reproducing process where new bubble universes are constantly budding off from the eternally inflating background. This is often called the eternal inflationary multiverse, or sometimes a level 2 multiverse in Max Tegmark's classification system. Each bubble universe could be incredibly vast, perhaps even infinite in itself, and completely causally disconnected from all the others, meaning we could never reach them or communicate with them as the space between them is expanding faster than light. Within this eternal inflation framework, different bubble universes might end up with different physical properties. As each bubble pinches off from the inflating vacuum, the fundamental constants of nature, like the strength of gravity, the mass of an electron, or the speed of light, might settle into different values. Imagine a cosmic lottery where each new universe gets a different set of winning numbers for its physical laws. Some universes might be radically different from ours, perhaps too chaotic or too simple to support any form of complexity or life. Others might be similar, and a few, by chance, might have just the right conditions for stars, galaxies, and perhaps even conscious observers to emerge like our own. This idea links to the anthropic principle, which we might touch upon later, suggesting that we find ourselves in a universe with these particular constants simply because these are the constants that allow for our existence. Another variation on this theme is the chaotic inflation model, proposed by Andre Linde. Here, the inflating field can take on different values in different regions, leading to a fractal-like structure of inflating and non-inflating domains. Our universe would be just one such domain. Think of it like a giant, ever-expanding foam, where each bubble in the foam is a universe, and the foam itself is the eternally inflating space. Some theories even suggest that the vacuum energy, the energy of empty space which drives inflation, could decay from a high-energy state to lower energy states in different ways in different bubbles. If our universe is in a false vacuum state, it might one day catastrophically transition to a true lower-energy vacuum, fundamentally altering its laws of physics, though this is highly speculative and not something to worry about for sleep. The key takeaway from these inflationary multiverse theories is the idea of a vast dynamic cosmic process that naturally and perhaps inevitably churns out an immense, perhaps infinite number of diverse universes, our own being just one unremarkable member of this grand cosmic ensemble. The ongoing debate here is whether eternal inflation is a necessary consequence of our best inflationary models, and if so, how we might ever find indirect evidence for such an unobservable collection of other worlds. As we drift further into the possibilities of multiple realities, we encounter a set of multiverse theories that spring not from the grand scales of cosmic inflation, but from the strange and often baffling rules of the quantum realm itself, the world of atoms and subatomic particles. Remember how quantum mechanics tells us that before a measurement, a particle can exist in a superposition of multiple states at once. For example, an electron might be in a superposition of being in several locations simultaneously, or having its intrinsic spin pointing both up and down at the same time. The act of measurement, according to the traditional Copenhagen interpretation, forces the particle to choose one definite state, and its wave function, which described all the possibilities, collapses. The many worlds interpretation, MWI, which we touched upon in our quantum mysteries journey, offers a radical alternative to this collapse. Proposed by Hugh Everett III, MWI suggests that the wave function never collapses. Instead, every time a quantum measurement or interaction occurs that has multiple possible outcomes, the entire universe splits, or branches, into a set of parallel universes. Each of these newly formed universes corresponds to one of the possible outcomes. So if an electron could be found in position A or position B, upon measurement, the universe splits into one branch where the electron is found at A, and another distinct branch where it's found at B. You, as the observer, also split along with the universe. In one branch you see the electron at A. In another, an identical copy of you sees it at B. Both outcomes occur, each in its own reality. Imagine you're at a crossroads in a choose-your-own-adventure story. Instead of picking one path, the MWI suggests that reality itself splits, and one version of you goes down path A, while another version of you simultaneously goes down path B. Both adventures unfold, but in separate, non-interacting storylines or universes. This branching happens constantly, with every quantum event that has more than one potential outcome, leading to an unimaginably vast, ever-diverging tree of parallel worlds. Our perception of a single, definite reality is simply because our consciousness is confined to following one particular path, one specific branch, through this immense multiverse. There's no special collapse mechanism needed. The deterministic evolution of the universal wave function, as described by the Schrödinger equation, is all there is. The appeal of MWI lies in this mathematical elegance and its avoidance of the somewhat ad hoc collapse postulate. However, the sheer ontological extravagance of an infinite number of constantly splitting universes is a major hurdle for many, and scientists still debate how to properly derive the probabilistic rules of quantum mechanics, the Born rule, from within the MWI framework, and whether it's truly testable. Another related idea from the quantum realm is the concept of consistent histories, or decoherent histories. This approach, developed by physicists like Robert Griffiths, Roland Omnes, Murray Gell-Mann, and James Hartley, attempts to assign probabilities to entire sequences of quantum events, or histories, without necessarily invoking a collapse or observers. It focuses on identifying sets of histories that are internally consistent and decohere from each other, meaning they don't quantum mechanically interfere. In this framework, one might consider different possible stories of the universe, each with a certain probability. While not always explicitly framed as a multiverse theory, in the same way as MWI. It can be interpreted as suggesting that many different consistent narratives of reality might unfold, and we just happen to experience one of them. The challenge lies in defining which sets of histories are real or meaningful. Then there's the idea of many minds interpretation, a variation or extension of MWI. Instead of the physical universe splitting, some proponents suggest that it's the observer's mind or consciousness that splits into different states, each perceiving a different outcome. The physical world remains singular, but there are multiple streams of consciousness associated with it. This tries to address some of the perceived awkwardness of physical universe splitting, but introduces its own set of philosophical complexities regarding the nature of mind and its relation to the physical world. We could also consider transactional interpretations of quantum mechanics, like the one proposed by John Cramer. This model describes quantum interactions as a handshake between an offer wave, traveling forward in time from the emitter, and a confirmation wave, traveling backward in time from the absorber. While not inherently a multiverse theory, it plays with the nature of time and causality in ways that could, in some extensions or philosophical ponderings, hint at alternative timelines or realities that are attempted, but not actualized, in our experience sequence of events. Similarly, pilot wave theories like Bohmian mechanics propose that particles have definite positions and are guided by a quantum wave. This is deterministic, but if one considers all the possible initial configurations of particles and their guiding waves, one might imagine a multiverse of all possible Bohmian trajectories, though only one is our actual universe. The core mystery in all these quantum-inspired multiverse ideas is how to reconcile the probabilistic nature of quantum outcomes with our experience of a single, seemingly definite world, and whether the other possibilities are somehow just as real. Leaving the quantum realm for a moment, let's now ascend into the highly theoretical and mathematically intricate world of string theory, which offers its own distinct and rather spectacular visions of a multiverse. String theory in its various forms, like M-theory, is an ambitious attempt to be a theory of everything, a single framework that can unify all the fundamental forces of nature, including gravity and all the fundamental particles, by proposing that the ultimate constituents of reality are not point-like particles, but unimaginably tiny, one-dimensional vibrating strings. Different vibrational modes of these strings, much like the different notes produced by a guitar string, correspond to different types of particles with different properties: mass, charge, spin. One of the most striking features of string theory is that for its mathematical consistency, it requires the existence of extra spatial dimensions beyond the three we perceive: length, width, height, plus time. Most versions of string theory predict a total of 10 or 11 space-time dimensions. So where are these extra dimensions? The prevailing idea is that they are compactified, meaning they are curled up into incredibly tiny, complex shapes, far too small for us to see or directly interact with. Imagine a garden hose. From a great distance, it looks like a one-dimensional line, but if you get very close, you realize it has a second circular dimension curled around it. The extra dimensions in string theory are thought to be curled up in a similar, albeit far more complex way, at every point in our familiar 3D space. The precise geometry of these compactified dimensions, often described by intricate mathematical structures known as Calabi-Yau manifolds, is crucial because it determines the vibrational modes of the strings, and thus the types of particles and the fundamental constants of physics that we observe in our universe. This leads us to the string theory landscape. It turns out that there isn't just one unique way to compactify these extra dimensions. The equations of string theory seem to allow for an enormous number, perhaps 10 to the power of 500, that's a 1 followed by 500 zeros, or even more, distinct vacuum states or ways these dimensions can be curled up. Each of these solutions would correspond to a universe with its own unique set of physical laws, constants, and particle types. Our universe, with its specific values for the strength of gravity, the mass of the electron, etc., would just be one tiny, perhaps randomly selected, point in this vast landscape of possibilities. This provides another avenue for a multiverse. Each stable valley in this landscape could represent a different type of universe, perhaps existing as separate bubbles formed during eternal inflation, as we discussed earlier, with string theory dictating the menu of possible physics for each bubble. Scientists still debate whether this landscape is a feature or a bug of string theory. Does it predict too much, making it untestable, or does it naturally explain the fine-tuning of our own universe via the anthropic principle? Then there's the concept of brain worlds, which arises from M-theory, an extension of string theory that incorporates higher dimensional objects called brains, short for membranes. In this picture, our entire three-dimensional universe might be a three-brain, a vast extended membrane existing within a higher dimensional space called the bulk. We and all the particles and forces of the standard model, except possibly gravity, would be confined to this brain, like characters drawn on a sheet of paper, unable to directly access the extra dimensions of the bulk. However, gravity, according to some brain world scenarios, might be able to leak into or propagate through these extra dimensions. This could explain why gravity appears so much weaker than the other fundamental forces. The exciting part for multiverse theories is that there could be other brains, other parallel universes, also existing in this higher dimensional bulk, perhaps very close to our own brain in the extra dimensions, yet invisible to us. Imagine two parallel sheets of paper, floating close together in a 3D room. Beings confined to one sheet might be completely unaware of the other, unless something could travel between the sheets. Some brain world models even propose scenarios where these brains could collide, an event that might trigger a big bang on each brain, leading to a cyclic or ekpyrotic model of the universe, which we'll touch upon. There's also the idea of hidden sector brains, parallel universes that interact with ours only very weakly, perhaps only through gravity or other exotic, undiscovered forces. The exact geometry and number of these extra dimensions, and the properties of the brains within them, are still highly speculative, part of the ongoing research in string theory. The sheer mathematical complexity makes definitive predictions difficult, but the framework undeniably opens up a rich tapestry of possibilities for universes beyond our own, intricately linked to the very fabric of extra-dimensional space. Beyond the continuous creation of universes through eternal inflation or the quantum branching of realities, there lies another fascinating class of multiverse theories. Those that propose our universe is not a one-time event, but part of an endless series of cosmic rebirths. These are the cyclic universe models. Instead of a single Big Bang marking the absolute beginning of time, these models envision a universe that undergoes an infinite sequence of expansions and contractions, or bangs followed by crunches or other transformative events, with each cycle potentially creating a new iteration of the cosmos, perhaps with similar or even different physical properties. One of the older ideas in this vein is the oscillating universe theory. In this picture, the universe expands after a Big Bang, but eventually the gravitational pull of all its matter halts the expansion and causes it to start contracting. This contraction continues until all matter collapses into an incredibly dense state, a big crunch, which then somehow bounces and re-explodes into a new Big Bang, starting a new cycle of expansion. Imagine a cosmic lung, endlessly inhaling and exhaling, each breath a new universe. However, classical oscillating universe models faced significant problems, particularly with the buildup of entropy disorder, from one cycle to the next, which would seem to make the cycles progressively longer and larger, not truly identical or endlessly repeating in a simple way. Also, our current observations suggest the universe's expansion is accelerating, driven by dark energy, which makes a future gravitational collapse seem unlikely unless the nature of dark energy changes. More modern cyclic models, often incorporating ideas from string theory and brain cosmology, have attempted to address these issues. One prominent example is the ekpyrotic universe model, from the Greek word ekpyrosis, meaning conflagration or cosmic fire, and its closely related cyclic model developed by Paul Steinhardt and Neil Turok. In these scenarios, our universe is envisioned as one of two parallel brains existing in a higher dimensional space. Remember those from our string theory discussion? These two brains are not static, but are slowly moving towards each other through the extra dimension. The Big Bang in our universe in this picture is not a singularity or an absolute beginning, but rather the result of a gentle collision or clash between our brain and the other parallel brain. This collision releases an enormous amount of energy, heating up our brain and filling it with matter and radiation, effectively resetting the universe and starting a new phase of expansion and cooling, much like the standard Big Bang model describes. After the collision, the brains move apart again, cool down, and the universe expands, eventually becoming dilute and empty as dark energy dominates. But then some force, perhaps related to the extra dimension itself, draws the brains back together again, leading to another collision, another bang, and the start of a new cycle. Each cycle could last trillions of years. This model avoids the singularity problem of the standard Big Bang, and can also address issues like the flatness and uniformity of the universe, without needing cosmic inflation in the same way, though some versions incorporate a modified inflationary phase. The nearly empty state of the universe at the end of each cycle helps to reset the entropy, allowing for more consistent repetitions. Another related idea is conformal cyclic cosmology, CCC, proposed by Roger Penrose. This is a more mathematically abstract model. Penrose suggests that at the very end of our universe's expansion, when all matter has decayed, and only photons and perhaps other massless particles remain, the universe becomes effectively scale-invariant or conformally invariant. At this point, the vast, empty, cold future of one aeon, a cosmic cycle, can be mathematically identified through a conformal transformation with the incredibly dense hot Big Bang state of the next aeon. So, the end of one universe seamlessly becomes the beginning of another, in an infinite chain. In this view, evidence from the previous eon might even be detectable in the cosmic microwave background radiation of our current aeon, a claim that has generated much debate and scrutiny among cosmologists. These cyclic models offer a profound alternative to a universe with a singular beginning. They paint a picture of an eternal cosmos, constantly reinventing itself, perhaps learning or evolving with each iteration, or perhaps just playing out endless variations on a cosmic theme. Scientists are still actively researching whether these models are consistent with all observational data, and whether their underlying theoretical assumptions, like the existence of brains and extra dimensions, or the specific behavior of fields at extreme energies, are valid. The allure of an eternal, self-renewing cosmos, however, continues to inspire these fascinating explorations into universes that might have existed before ours and those that might come after, in an endless, rhythmic dance of cosmic creation and rebirth. Let's now drift into a realm where the distinction between the physical universe and the abstract world of mathematics begins to blur, giving rise to some truly mind-expanding, if highly philosophical, multiverse concepts. What if the reason our universe seems to be so exquisitely described by mathematics is not just that math is a useful tool for understanding it, but that the universe is, in some fundamental sense, a mathematical structure? And if that's the case, what about all other possible mathematical structures? This leads us to the mathematical universe hypothesis, MUH, most prominently championed by physicist Max Tegmark. The MUH proposes that our external physical reality is essentially a mathematical structure, and that, more radically, all mathematical structures that are self-consistent exist physically as separate universes. In this view, mathematics is not just something humans invented or discovered to describe the universe. Mathematics is the universe, or rather, a universe. Our universe, with its specific set of particles, forces, and dimensions, corresponds to one particular, very complex mathematical structure. But any other self-consistent mathematical structure, from simple geometric shapes to incredibly elaborate abstract algebras or topological spaces, also describes a genuine, physically existing parallel universe. Imagine a vast library containing every possible book that could ever be written using a given alphabet and grammar rules, where each book represents a different mathematical structure. The MUH suggests that every one of these books is not just a description, but an actual existing world. Our universe is just one very long, very specific novel in this infinite library. Other novels might describe universes with different numbers of spatial dimensions, different fundamental particles, or even entirely different kinds of physical laws, as long as their underlying mathematical description is free of contradictions. This is Tegmark's Level 4 Multiverse, the ultimate ensemble of all mathematically possible realities. It's the most diverse kind of multiverse imaginable, encompassing not just variations on our type of physics, but entirely alien forms of existence governed by completely different mathematical principles. The MUH attempts to address deep philosophical questions like, why this particular universe with these particular laws? Its answer is that there's nothing special about our universe's laws. All possible, mathematically consistent laws exist somewhere. We find ourselves in this one because it's complex enough and stable enough to allow for the evolution of self-aware substructures, like us, capable of observing it. This is a strong form of the anthropic principle. One of the challenges for the MUH is the measure problem. If all mathematical structures exist, how do we assign probabilities or explain why we find ourselves in this particular type of universe rather than an infinitely simpler and perhaps more common one? How do we derive the observed complexity and physical laws from the set of all mathematical possibilities? Related to this, but perhaps a step less abstract, is the idea of the simulated universe or simulation hypothesis. This proposes that our reality, including ourselves and everything we perceive, might be an incredibly advanced computer simulation created by a more fundamental, base reality, or perhaps by another simulation within a chain of simulations. If it's possible for a civilization to develop technology capable of simulating consciousness and entire universes with convincing fidelity, then, some argue, it's statistically likely that we are living in such a simulation, because many more simulated universes would likely be created than real base universes. Think of the incredibly detailed and immersive video games or virtual reality environments we are beginning to create. Now imagine a civilization far more advanced than ours, with computational power beyond our wildest dreams. Could they create a simulation so perfect that its inhabitants wouldn't know they were simulated? The philosopher Nick Bostrom formalized this into the simulation argument, which suggests that at least one of three propositions is true. 1. Civilizations almost always go extinct before reaching a stage where they can create such simulations. 2. Civilizations that reach this stage are, for some reason, uninterested in running such simulations. Or 3. We are almost certainly living in a computer simulation. If we are in a simulation, then our universe's laws of physics are essentially the codes or the rules programmed by our simulators. This could explain why our universe seems to have discrete, quantifiable properties, like quantum mechanics suggests, and why it can be described by mathematics, because it's fundamentally computational. The simulation hypothesis raises a cascade of unsettling and fascinating questions. Who are the simulators? What is their purpose? Can we find glitches in the matrix, evidence that our reality is not fundamental? And if our universe is a simulation, is it just one of many, perhaps running on different servers, or with different parameters, constituting a multiverse of simulated worlds? Could we ourselves one day create simulated universes, leading to an infinite recursion of realities within realities? Scientists and philosophers debate whether the simulation hypothesis is testable or purely speculative. Some have proposed looking for evidence of the underlying grid or computational structure of our reality, or for physical laws that seem optimized in a way a programmer might design them. For now, it remains a deeply thought-provoking, if somewhat unnerving, possibility that our entire existence might be an elaborate digital construct, one of potentially many such creations, a dream within a dream, a story playing out on a cosmic hard drive. Let's now turn our attention to some of the most gravitationally extreme objects in our own universe, black holes, and consider the speculative yet intriguing theories that suggest these cosmic behemoths might themselves be gateways or even progenitors of new universes. A black hole, as you may know, is a region of space-time where gravity is so incredibly strong that nothing, not even light, can escape once it crosses a certain boundary called the event horizon. At the very center of a black hole, according to classical general relativity, lies a singularity, a point of infinite density and zero volume where the known laws of physics break down. This breakdown is a strong indication that we need a theory of quantum gravity to understand what truly happens there. One fascinating idea, sometimes called fecund universes, or black hole cosmology, proposed by physicist Lee Smolin and others, suggests that every time a black hole forms in a parent universe, a new baby universe might be created on the other side of its singularity. In this scenario, the conditions within a collapsing star that forms a black hole might trigger a sort of rebound or a new Big Bang-like event, but one that is causally disconnected from the parent universe, expanding into its own new region of space-time. The physical constants in this new baby universe might be slightly different from those in the parent universe. Smolin further proposed a kind of cosmological natural selection, universes that happen to have physical constants that lead to the formation of many black holes, and thus produce many offspring universes, would become more common in the overall multiverse. If our universe is particularly good at making black holes, perhaps it's because its parameters have been selected for this fecundity over many cosmic generations. This theory attempts to provide a naturalistic explanation for the apparent fine-tuning of our universe's constants without directly invoking the anthropic principle. The debate here centers on the unknown physics of singularities and whether such a universe creation mechanism is plausible or even theoretically coherent without a full theory of quantum gravity. Another related idea comes from the concept of eternal black holes. In certain mathematical solutions of Einstein's equations, like the maximally extended Schwarzschild or Kerr spacetimes. These idealized mathematical models sometimes feature structures like white holes, the time-reversed version of a black hole from which matter and light can only escape, not enter, or wormholes and tunnels connecting different regions of space-time or even different universes. While most physicists believe that realistic black holes formed from collapsing stars probably don't lead to stable wormholes or white holes that could connect to other universes due to instabilities and the need for exotic matter with negative energy density to keep a wormhole open, these mathematical possibilities keep the idea alive in theoretical explorations. Perhaps in a full theory of quantum gravity, the singularity is resolved or bounces in a way that does create a traversable connection or a new expanding region. Then there's the notion of universes being created from quantum fluctuations in a pre-existing nothingness or a metaverse. We talked about how the quantum vacuum is a seething sea of virtual particles. Some theories, like those explored by Alexander Vilenkin, propose that an entire universe, with all its space, time, matter, and energy, could spontaneously arise as a quantum fluctuation from a state of nothing, where nothing does not mean absolute non-existence, but perhaps a state without classical space-time, a sort of quantum foam. If this can happen once, why not many times, leading to a multiverse of spontaneously generated universes? This is sometimes called creation ex nihilo, creation out of nothing, in a quantum context. The probability of such an event for a universe as large as ours might be incredibly small, but if the underlying metaverse, or quantum substrate, exists for an infinite time or is infinitely vast, then even highly improbable events become inevitable. We could also consider the no-boundary proposal by Stephen Hawking and James Hartley for the origin of the universe. This uses quantum mechanics to describe the universe's very beginning, suggesting that space-time, when you go back far enough, becomes fuzzy and loses its classical character, eventually having no discernible edge or beginning in time, much like the surface of a sphere has no edge. While this primarily describes our universe, if the conditions that allow for such a no-boundary origin are not unique, then perhaps many such universes could come into being, each with its own self-contained space-time, originating from a quantum probabilistic state. These theories, linking the birth of universes to the most extreme gravitational phenomena or to the fundamental quantum nature of reality, are at the very edge of scientific speculation. They rely on physics that we don't yet fully understand, the physics of singularities, the true nature of the quantum vacuum, and the rules of quantum gravity. However, they offer tantalizing glimpses into how our universe might not be a solitary creation, but potentially part of a much grander cosmic ecology, where universes are born, perhaps give birth to others, and exist within a vast, interconnected web of cause and effect, or spontaneous generation, far beyond our current observational reach. The mystery of what truly lies at the heart of a black hole, or what preceded our Big Bang, remains a powerful driver for these imaginative and profound cosmological ideas. Let's now float into a set of multiverse ideas that challenge our very perception of dimensionality and reality itself, those inspired by the holographic principle. The holographic principle is a rather mind-bending concept that originated from studies of black hole thermodynamics and string theory. In essence, it suggests that the information content of a volume of space can be entirely described or encoded on a lower dimensional boundary surrounding that volume, much like a three-dimensional image, a hologram, can be encoded on a two-dimensional surface, a holographic plate. Imagine you have a room. The holographic principle suggests that everything happening inside that 3D room, all the objects, all the events, all the information, could in principle be perfectly described by information written on the 2D walls, floor and ceiling of that room. It's not that the room is the walls, but that the walls contain all the necessary data to reconstruct the 3D reality within. This idea, if applied to our entire universe, has profound implications. It could mean that our three-dimensional universe, the one we experience with all its depth and volume, might actually be a holographic projection of information stored on a distant, two-dimensional boundary surface, perhaps at the cosmic horizon, the edge of the observable universe. We would be like characters in an incredibly sophisticated hologram, perceiving three dimensions, while the real information describing us exists on a flat, faraway screen. This doesn't mean our universe is an illusion in the sense of not being real, but rather that its fundamental description might be simpler, or at least lower dimensional than it appears. The physicist Gerard 't Hooft first proposed something like this, and it was later given a more precise formulation in the context of string theory by Leonard Susskind, particularly through the ADS-CFT correspondence, anti-de Sitter conformal field theory correspondence, also known as Maldacena duality, or gauge-gravity duality. This is a powerful and concrete mathematical conjecture that relates a theory of gravity in a certain type of higher dimensional curved spacetime called anti-de Sitter space, ADS, to a quantum field theory, without gravity, existing on its lower dimensional boundary, a conformal field theory, CFT. It's a duality because it means these two seemingly very different theories are, in a deep mathematical sense, equivalent, different descriptions of the same underlying physics. Calculations that are very difficult in one theory can sometimes be translated and performed much more easily in the other. So how does this lead to a multiverse? If our universe can be described as a hologram projected from a boundary, then one could imagine other different holographic projections arising from different boundary conditions or different screens. Perhaps there are multiple such boundary surfaces, each encoding its own distinct universe. Or if the underlying bulk spacetime, the higher dimensional space where the boundary resides, is vast enough, different regions of the boundary could project different holographic universes. Some theories even speculate about nested holograms, where one holographic universe might contain information that projects another, and so on. Another way to think about a holographic multiverse is to consider the information content of the universe. The holographic principle sets a limit on the maximum amount of information, or entropy, that can be contained within a given region of space, and this limit is proportional to the area of its boundary, not its volume, which is counterintuitive. If there are fundamental limits to information density, and if information is what ultimately constitutes reality, then different configurations of this fundamental information on different boundaries could correspond to different universes. The exact nature of this cosmic screen or boundary surface is, of course, highly speculative and depends on the specific theoretical model. It might be at the edge of our observable universe, or it might be related to more abstract concepts in quantum gravity. The idea also connects to black hole physics, as the entropy of a black hole, a measure of its information content, is proportional to the area of its event horizon, not its volume, which was one of the first hints towards the holographic principle. Some have even speculated that what we perceive as the Big Bang might have been the moment our universe was projected or encoded onto its boundary. The holographic principle challenges our most basic intuitions about space, volume, and information. It suggests that the three-dimensional world we inhabit might be a kind of elaborate illusion, a rich and complex tapestry woven from threads of information originating from a lower-dimensional reality. If this is true for our universe, it opens the door to the possibility of countless other such cosmic projections, each a self-contained world, perhaps existing parallel to ours, all arising from the fundamental interplay of information and geometry on some vast, unseen cosmic boundary. Scientists are still deeply exploring the implications of this principle and whether it provides a true key to understanding quantum gravity and the ultimate nature of reality, or if it's a fascinating mathematical correspondence that points towards something even stranger. Let's venture now into what might be considered the most abstract and philosophically driven class of multiverse theories, where the existence of other universes is postulated not necessarily from specific physical mechanisms like inflation or string theory, but from fundamental principles of mathematics, logic, or even metaphysics. These ideas push the boundaries of what we can even conceive of as a universe. One of the most encompassing is the mathematical universe hypothesis, MUH, or ultimate ensemble theory, which we touched upon when discussing simulated realities, but it deserves a deeper look in this philosophical context. Championed by Max Tegmark, the MUH proposes that all structures that exist mathematically also exist physically. Our universe, with its specific physical laws and constants, is just one particular mathematical structure among an infinite number of others. In this view, mathematics is not merely a tool that humans use to describe reality. Mathematics is reality at its most fundamental level. Every self-consistent mathematical equation, every possible geometry, every abstract algebraic system corresponds to a physically real universe. Imagine a vast infinite library where every conceivable mathematical textbook is present. The MUH suggests that each of these textbooks doesn't just contain descriptions, it is a universe. Some of these universes might be incredibly simple, perhaps a universe described by the geometry of a perfect sphere, or one governed by the rules of a basic number theory. Others, like ours, would be described by vastly more complex mathematical structures that allow for intricate phenomena like particles, forces, galaxies, and even self-aware beings who can discover the mathematical laws governing their own existence. This is Tegmark's Level 4 multiverse, the grandest and most diverse of them, all-encompassing not just universes with different physical constants, like in inflationary or string theory multiverses, but universes with entirely different kinds of physics, or even physics, that would be unrecognizable to us, governed by entirely alien mathematical principles. The core idea is that if a mathematical structure is well-defined and internally consistent, then it has an independent physical existence. The ongoing debate here revolves around how to test such a profound claim, how to understand the measure problem, why we find ourselves in this specific complex mathematical structure rather than a simpler one, and what physical existence even means for a purely mathematical entity. Another philosophical avenue to a multiverse is through modal realism, most famously articulated by philosopher David Lewis. Modal realism is the thesis that our actual world is only one among a vast plurality of other possible worlds. When we say something is possible, for example, it's possible that I could have chosen a different career, modal realism takes this literally. It suggests that there exists another concrete world, just as real as ours, where a counterpart of you did choose that different career. Every way the world could have been is a way some world is. These possible worlds are not abstract entities or mere ideas. They are concrete, existing universes, causally isolated from each other. So if it's logically possible for a universe to exist with slightly different laws of physics, or where dinosaurs never went extinct, or where you made a different decision this morning, then according to modal realism, such a universe genuinely exists. This is not necessarily driven by physics, but by a philosophical analysis of what possibility and actuality mean. The sheer number of such possible worlds would be staggering, encompassing every conceivable variation and alternative history. Critics often find this ontological extravagance hard to accept and debate the nature of counterparts in other worlds. Then there are ideas that arise from considering the nature of information and computation. If our universe can be described as a vast computation, as the simulation hypothesis suggests, or as some interpretations of physics imply, then perhaps other computations, other algorithms, could also generate self-contained realities. The computational universe, an idea, suggests that any process complex enough to simulate or embody consciousness could be considered a universe from the perspective of that consciousness. This could lead to a multiverse of computational realities, some simple, some incredibly complex, some running on physical substrates like ours, others perhaps on more exotic computational platforms. We might also consider fictional realism as a very fringe philosophical idea, suggesting that perhaps even the consistent worlds described in works of fiction could have some form of existence, if only as complex informational structures. While this is far from mainstream science, it touches upon the deeper question of what criteria something must meet to be considered real. If a world is internally consistent and richly described, what makes it less real than a distant, unobservable bubble universe predicted by a speculative physical theory? These more philosophical multiverse concepts force us to confront the limits of our definitions of universe and existence. They challenge us to think about whether physical instantiation is the only criterion for reality, or whether mathematical consistency, logical possibility, or informational complexity might also give rise to forms of existence that are in their own way just as valid as our own perceived world. As you drift with these abstract notions, let your mind play with the idea that reality might be far vaster and more varied than anything our current physics can describe, perhaps encompassing all that can be consistently imagined or mathematically formulated. Section 9. As we navigate this vast ocean of multiverse theories, a recurring question arises, particularly when considering universes with potentially different physical laws or constants. Why does our universe appear to be so exquisitely fine-tuned for the existence of life, or at least for the existence of complex structures like stars and galaxies? Many of the fundamental constants of nature, the strength of gravity, the charge of an electron, the mass of a proton, the value of the cosmological constant related to dark energy, seem to have values that fall within a very narrow range that allows for a universe capable of developing complexity. If these constants were even slightly different, the universe might have been radically different and inhospitable. Perhaps stars would never have formed, or atoms couldn't exist, or the universe might have recollapsed immediately after the Big Bang, or expanded too quickly for any structures to coalesce. This apparent fine-tuning is a puzzle. Is it just a lucky coincidence that the constants happen to be what they are? Did a creator deliberately set these values, or is there a more naturalistic explanation? Many multiverse theories offer a potential solution to this fine-tuning problem through what is known as the anthropic principle, or more specifically, the weak anthropic principle, WAP. The WAP essentially states that the observed values of physical and cosmological quantities are not equally probable, but take on values restricted by the requirement that there exist sites where carbon-based life, or more generally, complexity and observers, can evolve, and that the universe be old enough for it to have done so. In simpler terms, we observe the universe to be the way it is, with these specific fine-tuned constants, because if it were any different in crucial ways, we wouldn't be here to observe it. Now, if our universe is the only universe that exists, then invoking the WAP to explain fine-tuning might seem a bit circular or unsatisfying. It just states that things are the way they are because we're here. However, if our universe is just one among a vast ensemble of other universes, perhaps an infinite number of them, as many multiverse theories, like eternal inflation or the string theory landscape, Suggest then the WAP gains much more explanatory power. In this anthropic multiverse scenario, imagine that all these other universes exist, but they have different values for their fundamental constants, randomly scattered across a wide range of possibilities. The vast majority of these universes would likely be sterile, with conditions completely unsuitable for the formation of stars, planets, or any form of complex life. They might be short-lived or devoid of chemical complexity, or too chaotic. However, within this immense collection of universes, there would inevitably be some, perhaps a very small fraction, where the constants just by chance happen to fall within the narrow life-permitting range. It is only in these kinds of universes that observers like us could evolve and ask questions about why the constants are so finely tuned. So, we find ourselves in a universe that appears fine-tuned, not because it was uniquely designed for us, or because of some incredible cosmic luck in a single shot, but simply because our existence is a selection effect. We can only exist in a universe that has the properties compatible with our existence. All the other failed or sterile universes are out there, unobserved by beings like us, because they lack the necessary conditions. Think of it like this. Imagine a vast field where a machine is randomly scattering seeds, but also randomly setting the soil conditions, acidity, moisture, nutrients, in different patches. Most patches might have terrible soil and no seeds will sprout. But in a few rare patches where the soil conditions happen to be just right, seeds will grow into plants. If you are a sentient plant in this field, you might marvel at how perfectly your little patch of soil is suited for your growth. The anthropic multiverse explanation would be that you only find yourself in that good patch. Because it's a good patch. You wouldn't exist to ponder it in any of the bad patches. Our universe is like that good patch of soil. This anthropic reasoning in a multiverse context is a powerful idea, but it's also controversial. Some scientists see it as a legitimate scientific explanation for fine-tuning, a natural consequence of certain multiverse theories. Others criticize it as being untestable, or even a give-up on finding deeper, more fundamental explanations for why the constants have the specific values they do. They argue that science should strive for predictive theories, not just post hoc explanations based on our own existence. The debate also touches on what constitutes life or complexity. Are we too narrowly focused on carbon-based life? Could other forms of complexity or observation arise in universes with vastly different physics? These are ongoing discussions. For now, the possibility that our universe's life-friendly properties are a consequence of our being one lucky draw in a vast cosmic lottery of many different worlds remains a profound and thought-provoking implication of many multiverse theories. A gentle reminder that our existence might be both a product of chance and a necessity, given the vastness of what could be. Let's now consider a type of multiverse that arises not necessarily from exotic physics like string theory or quantum branching, but from the sheer, mind-boggling scale that our own universe might possess, potentially combined with the probabilistic nature of how matter arranges itself. This is often referred to as the quilted multiverse, or Tegmark's Level 1 multiverse, and it's arguably the least speculative, as it relies on assumptions that many cosmologists consider quite plausible. Namely, that space is infinite, or at least vastly larger than our observable horizon, and that the distribution of matter and energy on very large scales is roughly uniform. Imagine our observable universe, that sphere of space about 93 billion light-years across, from which light has had time to reach us since the Big Bang. This is our cosmic horizon, the limit of what we can currently see. But what lies beyond that horizon? Most cosmological models, including those based on inflation, suggest that space doesn't just end there. It continues on, perhaps infinitely. If space is indeed infinite, and if the fundamental laws of physics and the types of particles that can exist are the same everywhere, as our current observations within our horizon suggest, then a fascinating consequence emerges purely from probability. In an infinite space containing a finite number of possible ways that particles can be arranged within a given volume, a Hubble volume, roughly the size of our observable universe, it becomes statistically inevitable that arrangements of particles identical to those in our own Hubble volume must eventually repeat. Think of it like shuffling an infinitely large deck of cards, containing only a finite number of distinct card types. If you deal out hands of a certain size, you are bound to eventually deal out an identical hand. Similarly, if you have an infinite universe with a finite number of quantum states that particles can occupy within a region the size of our observable universe, then every possible configuration of those states, including the exact configuration that makes up our Hubble volume with you, me, the Earth, and everything else in it, must eventually repeat elsewhere. This means that if space is truly infinite and the distribution of matter is, on average, uniform, then somewhere out there, far beyond our cosmic horizon, there exists another region of space identical to ours. And not just one, but infinitely many such identical regions, or Hubble patches. In these distant patches, there would be another Earth, another you, living a life identical to yours up to this very moment. There would also be regions that are almost identical, but where you made a different choice this morning, or where some minor historical event played out differently. And there would be regions that are vastly different. All possible variations of our observable universe, consistent with the initial conditions and laws of physics in this overarching infinite space, would exist somewhere. This is the quilted multiverse, an infinite tapestry of Hubble volumes, some identical to ours, some slightly different, some wildly different, all existing within the same vast, perhaps infinite spatial expanse, governed by the same fundamental physical laws. Unlike some other multiverse theories, these other universes, or rather distant regions of our own vastly larger universe, are not in different dimensions or causally disconnected by a quantum split. They are simply very, very far away beyond our current ability to see or interact with them due to the finite speed of light and the expansion of space. The distances involved are truly astronomical, far beyond anything we can comprehend. Estimates for how far you'd have to travel to find your nearest identical copy vary wildly depending on the assumptions made about the number of possible quantum states, but they are typically numbers so large they dwarf any other number in science. Like 10 to the power of 10 to the power of 118 meters, a number known as a Googleplexian of sorts in this context. So while these other U's might exist, they are, for all practical purposes, completely inaccessible. The concept of a quilted multiverse relies on a few key assumptions: that space is infinite, or at least vastly larger than our horizon, that the laws of physics are uniform throughout this larger space, and that there's a finite number of ways matter can be arranged within a Hubble volume. If these assumptions hold, then the repetition of regions is a statistical inevitability. Scientists still debate the true extent of space. Is it genuinely infinite, or just incredibly large but finite, perhaps like the surface of a vast hypersphere? Current observations suggest space is very flat, which is consistent with it being infinite, but we can't know for sure. The idea also raises philosophical questions about identity. If an exact duplicate of you exists light years away, is that still you? What does it mean for your consciousness or your experiences? For our sleepy contemplation, though, it is a rather dizzying thought that the specific arrangement of particles making up your current reality, your thoughts, your memories, might not be unique in an infinite cosmos, but rather one pattern in an endless cosmic quilt, repeating over and over again across unimaginable distances. Our exploration of multiverse theories has so far touched upon universes born from cosmic inflation, quantum branching, the intricate geometries of string theory, and the statistical inevitability of repetition in an infinite space. Now, let's turn our attention more directly to the concept of higher spatial dimensions, beyond the three we experience, length, width, height, and how their potential existence could give rise to or accommodate various multiverse scenarios. We've encountered extra dimensions in the context of string theory and brane worlds, but the idea of dimensions beyond our perception has a broader appeal and appears in several different theoretical frameworks. The notion that our universe might have more than 3 spatial dimensions is not new. In the early 20th century, physicists Theodore Kaluza and Oscar Klein proposed a theory, Kaluza-Klein theory, that attempted to unify gravity and electromagnetism by postulating the existence of a tiny, curled-up fourth spatial dimension. They showed that if you write down Einstein's equations of general relativity in 5 space-time dimensions, 4 space 1 time, and then assume one of the spatial dimensions is compactified into a tiny circle, the equations effectively split into 2 sets: Einstein's usual 4-dimensional gravity equations plus Maxwell's equations for electromagnetism along with a scalar field. It was a remarkable idea, suggesting that a fundamental force like electromagnetism could be a manifestation of geometry in an extra, unseen dimension. While the original Kaluza-Klein theory had its problems and didn't fully succeed in unifying all forces, it laid the groundwork for the idea that extra dimensions could be real and could have profound physical consequences. As we saw, modern string theory and M-theory require even more extra dimensions, typically 6 or 7, for their mathematical consistency. These dimensions are usually assumed to be compactified into complex shapes called Calabi-Yau manifolds, and the specific geometry of these curled-up dimensions determines the properties of the particles and forces in our 3D world. If these extra dimensions exist, they provide a space in which other universes, perhaps other brains, as in M-theory, could reside. Our universe would be a 3-brain, but there could be other parallel brains floating nearby in this higher dimensional bulk space. These other brain universes might have different numbers of dimensions themselves. Perhaps they are 4 brains or 2 brains, or they might be 3 brains like ours, but with different physical laws determined by their own internal stringy configurations or their position within the bulk. Interactions between these brains, like collisions, could trigger big bangs, as in the ekpyrotic scenario. Or perhaps particles or forces from our brain could leak into the bulk, or particles from the bulk could interact weakly with our brain, providing a potential, though highly speculative, way to detect the presence of these extra dimensions or other brains. Beyond string theory, the idea of a higher dimensional hyperspace or bulk in which our universe is embedded appears in various cosmological models. Some theories propose that dark matter or dark energy, the mysterious components that make up most of the energy density of our universe, might be manifestations of gravitational effects from matter or energy existing in these extra dimensions, or even from interactions with other nearby universes in the bulk. For example, the Randall-Sundrum models are a type of brain world scenario where our universe is a brain in a 5-dimensional anti-de Sitter spacetime. These models can address certain problems in particle physics, like the hierarchy problem, why gravity is so much weaker than other forces, by allowing gravity to propagate into the extra dimension. If such higher dimensions are large enough, some models propose large extra dimensions that could be as big as a millimeter, though they would only be accessible to gravity. They could offer fascinating possibilities. Could particles from our universe escape into these dimensions? Could particles from other universes or the bulk enter ours? Some speculative theories even consider the possibility of information or energy transfer between brains, or even, in science fiction terms, travel. However, current experimental searches for signs of large extra dimensions, e.g. at particle colliders like the LHC, or through precision tests of gravity at short distances, have so far not yielded any definitive evidence. The concept of higher dimensions itself is hard to visualize. We are 3-dimensional beings, and our intuition is based on that. To imagine a 4th spatial dimension, think of how a 2D being living on a flat plane, a flatlander, would perceive a 3D object like a sphere passing through its plane. It would first see a point, then a growing circle, then a shrinking circle, then a point again, before it vanishes. Similarly, if a 4D object were to pass through our 3D space, we would only perceive 3D slices, or cross-sections of it. The full reality of the higher dimensional space would be beyond our direct perception. If other universes exist in these extra dimensions, they would be parallel to ours, not in our familiar 3D space, but along these unseen higher dimensional axes. The ongoing mystery is whether these extra dimensions are a mathematical convenience, a feature of a correct but as yet unproven theory like string theory, or a genuine aspect of physical reality that could one day be detected, potentially revealing a much vaster and more complex cosmic structure than our three spatial dimensions alone would suggest. As we continue our gentle survey of multiverse possibilities, let's consider a category of theories where universes are not necessarily pre-existing or eternally spawning, but rather they emerge from some more fundamental underlying reality, or they evolve over vast cosmic timescales, perhaps changing their properties in the process. These ideas often blur the lines between physics, information theory, and even philosophy. One intriguing concept is that of an emergent universe. In this view, space-time itself, and perhaps even the laws of physics as we know them, are not fundamental, but rather emergent properties of a deeper, more basic system. Much like the fluidity of water is an emergent property of the collective behavior of individual H2O molecules, which are not themselves fluid. If our universe is an emergent phenomenon, then perhaps other different universes could emerge from this same underlying substrate under different conditions or with different initial seeds. What could this substrate be? Some theories speculate it might be a network of quantum information, a quantum foam at the Planck scale, where space and time lose their meaning, or perhaps a purely mathematical or computational system, as we've touched upon. Imagine a vast, featureless ocean of pure potential. Under certain conditions, or due to random fluctuations, a stable pattern, a persistent structure, might emerge from this ocean. That structure could be a universe like ours. Other patterns, other universes with different properties, might also emerge and coexist, or perhaps emerge and then dissolve back into the substrate if they are not stable. This is related to ideas in condensed matter physics, where complex collective behaviors, like superconductivity or superfluidity, emerge from the interactions of many simple components. Could our universe, with all its complexity, be an emergent crystal, or a persistent excitation, in some fundamental cosmic field or network? The challenge for such theories is to define the nature of this underlying substrate and the rules by which universes emerge from it, and to explain why our particular universe emerged with the properties it has. Then there's the idea of evolving universes, which we briefly encountered with Lee Smolin's theory of cosmological natural selection via black holes. The core concept here is that universes might not just be static entities with fixed laws, but they might be able to change their fundamental parameters over time, or from one generation to the next, if universes can reproduce, as in the black hole progeny model. If there's a mechanism for universes to be born with slightly varied physical constants, and if some sets of constants are more successful, e.g., lead to longer-lived universes or universes that produce more offspring universes, then over many cosmic eons, the multiverse could become populated primarily by universes with these fitter parameters. Our universe's apparent fine-tuning for complexity, and life could then be seen as a result of this cosmic evolutionary process. This idea of evolving physical laws is highly speculative, as our current understanding of fundamental constants is that they are, well, constant. However, some theories do allow for the possibility that these constants might actually be slowly varying fields, or that they could have had different values in the very early universe or under extreme conditions. If such variation is possible, and if there's a mechanism for inheritance of these varied parameters into new universes, then a form of cosmic evolution could indeed occur. The debate here centers on what the mechanisms for variation and selection might be, and whether such a process could lead to the specific kind of fine-tuning we observe. We could also consider universes that emerge from information-theoretic principles. Some physicists and philosophers, like John Archibald Wheeler with his it-from-bit idea, have proposed that information might be more fundamental than matter or energy. In this view, physical reality emerges from the processing of information, from answers to yes-no questions at the most basic level. If this is the case, then different sets of fundamental bits, or different informational structures could give rise to different emergent realities, a multiverse of informational constructs. The simulation hypothesis can also be seen as a form of emergent universe, where our reality emerges from the computations of an underlying, more fundamental system. These concepts of emergent and evolving universes push us to think about what is truly fundamental. Is it space-time? Is it quantum fields? Is it information? Or is it something else entirely that we haven't yet conceived of? If our universe is not a fundamental entity, but an emergent or evolved one, then the possibility of other such emergent or evolved universes seems almost natural. They might be vastly different from ours, perhaps based on different emergent principles, or having evolved along different cosmic pathways. As you let your mind drift on these ideas, picture the cosmos not as a static collection of worlds, but as a dynamic creative process, a vast laboratory where realities can crystallize from a deeper potential, or where universes themselves can learn, adapt, and change over an immensity of time that dwarfs even the age of our own familiar cosmos. As our sleepy exploration of multiverse theories continues, we now venture into some of the more speculative and exotic conceptual territories. These are ideas that often push the boundaries of known physics, sometimes relying on hypothetical forms of matter or energy, or proposing unconventional cosmological scenarios that, while perhaps not widely accepted, still offer intriguing food for thought and highlight the sheer imaginative scope of human inquiry into the nature of reality. Many of these are less theories in the rigorous scientific sense, and more like what-if scenarios or conceptual frameworks that emerge when we extrapolate current ideas to their most extreme limits. One area of speculation involves universes with fundamentally different types of matter or forces than those in our standard model. We know our universe is primarily composed of ordinary matter, protons, neutrons, electrons, along with dark matter and dark energy, whose natures are still mysterious. What if other universes exist, where the dominant forms of matter are entirely different? Perhaps universes made of exotic baryons or strange forms of mirror matter that interact with our matter only very weakly, if at all. Some particle physics theories beyond the standard model predict the existence of new particles and forces. If these theories are realized in different ways in different cosmic domains, they could lead to universes with entirely different chemistries and physics. Imagine a universe where the strong nuclear force is much weaker, so atomic nuclei beyond hydrogen are unstable, or one where electromagnetism is the dominant long-range force instead of gravity. Such universes would be utterly alien to us, perhaps incapable of forming stars or planets as we know them, but they might host other forms of complexity we can't even imagine. Then there's the idea of universes existing in different phases of a fundamental underlying substrate, much like water can exist as ice, liquid, or steam. Or perhaps the fundamental stuff of reality can exist in various cosmic phases, and our universe is just one such phase. Transitions between these phases could be akin to Big Bangs or other cataclysmic events, leading to the formation of new universes with different effective laws. Some theories speculate about a pre-Big Bang era or a bounce from a previous cosmic phase, and if such phase transitions are possible, they might occur differently in different regions of a larger metastructure, leading to a multiverse of diverse cosmic phases. Consider also the more out-there speculations arising from trying to resolve paradoxes in physics or philosophy. For example, some interpretations of time travel paradoxes, like the grandfather paradox, have led to the idea that traveling to the past might cause the timeline to split, creating a new parallel universe where the altered events unfold without affecting the original timeline. While time travel itself is highly speculative and likely impossible in the way popular fiction depicts, the conceptual framework of branching timelines to resolve causal inconsistencies is a recurring theme that hints at a multiverse of alternative histories. We could also touch upon Boltzmann brain scenarios, though these are often considered more of a philosophical problem or a reductio ad absurdum for certain cosmological models rather than a desirable multiverse theory. The idea is that in a vast, old and chaotic universe or multiverse governed by statistical fluctuations, it might be statistically more probable for a single conscious brain, a Boltzmann brain, to spontaneously fluctuate into existence, complete with false memories of a past and a surrounding universe, than for an entire ordered universe like ours to arise. If such entities are more probable, Why do we find ourselves in this vast, complex, and seemingly ordered universe? Some multiverse theories that predict an infinite number of random fluctuations might lead to a universe dominated by these disembodied, delusional brains, which most find an unappealing and problematic consequence. This pushes theorists to find multiverse models that avoid such paradoxes. There are also more abstract mathematical or logical universes that some philosophers and mathematicians ponder. For instance, if one considers the set of all possible computer programs, some of these programs, if run, might generate simulations complex enough to be considered universes. This leads to a multiverse of all possible computations. Or one could imagine universes based on entirely different logical systems than our own classical logic. What would a universe governed by intuitionistic logic or paraconsistent logic, which allows for some contradictions, look like or behave like? These are deeply abstract and far from physics, but they illustrate the extent to which the concept of universe can be stretched when we remove our usual physical and observational constraints. These exotic and speculative realms are where our current understanding truly frays. They are the here-be dragons on the map of cosmological thought. They are often not well-formed theories, but rather imaginative explorations of the limits of possibility. However, even such far-flung ideas can sometimes inspire new avenues of more rigorous research or highlight hidden assumptions in our current models. As you drift in this sea of speculation, allow your mind to simply wonder at the sheer audacity of these concepts, the human capacity to imagine realities so profoundly different from our own, even if they remain firmly in the realm of what-if rather than established science. As our sleepy exploration of multiverse theories continues, we now venture into some of the more speculative and exotic conceptual territories. These are ideas that often push the boundaries of known physics, sometimes relying on hypothetical forms of matter or energy, or proposing unconventional cosmological scenarios that, while perhaps not widely accepted, still offer intriguing food for thought and highlight the sheer imaginative scope of human inquiry into the nature of reality. Many of these are less theories in the rigorous scientific sense, and more like what-if scenarios or conceptual frameworks that emerge when we extrapolate current ideas to their most extreme limits. One area of speculation involves universes with fundamentally different types of matter or forces than those in our standard model. We know our universe is primarily composed of ordinary matter, protons, neutrons, electrons, along with dark matter and dark energy, whose natures are still mysterious. What if other universes exist, where the dominant forms of matter are entirely different? Perhaps universes made of exotic baryons or strange forms of mirror matter that interact with our matter only very weakly, if at all. Some particle physics theories beyond the standard model predict the existence of new particles and forces. If these theories are realized in different ways in different cosmic domains, they could lead to universes with entirely different chemistries and physics. Imagine a universe where the strong nuclear force is much weaker, so atomic nuclei beyond hydrogen are unstable, or one where electromagnetism is the dominant long-range force instead of gravity. Such universes would be utterly alien to us, perhaps incapable of forming stars or planets as we know them, but they might host other forms of complexity we can't even imagine. Then there's the idea of universes existing in different phases of a fundamental underlying substrate, much like water can exist as ice, liquid, or steam. Or perhaps the fundamental stuff of reality can exist in various cosmic phases, and our universe is just one such phase. Transitions between these phases could be akin to Big Bangs or other cataclysmic events, leading to the formation of new universes with different effective laws. Some theories speculate about a pre-Big Bang era or a bounce from a previous cosmic phase, and if such phase transitions are possible, they might occur differently in different regions of a larger metastructure, leading to a multiverse of diverse cosmic phases. Consider also the more out-there speculations arising from trying to resolve paradoxes in physics or philosophy. For example, some interpretations of time travel paradoxes, like the grandfather paradox, have led to the idea that traveling to the past might cause the timeline to split, creating a new parallel universe where the altered events unfold without affecting the original timeline. While time travel itself is highly speculative and likely impossible in the way popular fiction depicts, the conceptual framework of branching timelines to resolve causal inconsistencies is a recurring theme that hints at a multiverse of alternative histories. We could also touch upon Boltzmann brain scenarios, though these are often considered more of a philosophical problem or a reductio ad absurdum for certain cosmological models rather than a desirable multiverse theory. The idea is that in a vast, old and chaotic universe or multiverse governed by statistical fluctuations, it might be statistically more probable for a single conscious brain, a Boltzmann brain, to spontaneously fluctuate into existence, complete with false memories of a past and a surrounding universe, than for an entire ordered universe like ours to arise. If such entities are more probable, why do we find ourselves in this vast, complex, and seemingly ordered universe? Some multiverse theories that predict an infinite number of random fluctuations might lead to a universe dominated by these disembodied, delusional brains, which most find an unappealing and problematic consequence. This pushes theorists to find multiverse models that avoid such paradoxes. There are also more abstract mathematical or logical universes that some philosophers and mathematicians ponder. For instance, if one considers the set of all possible computer programs, some of these programs, if run, might generate simulations complex enough to be considered universes. This leads to a multiverse of all possible computations, or one could imagine universes based on entirely different logical systems than our own classical logic. What would a universe governed by intuitionistic logic or paraconsistent logic, which allows for some contradictions, look like or behave like? These are deeply abstract and far from physics, but they illustrate the extent to which the concept of universe can be stretched when we remove our usual physical and observational constraints. These exotic and speculative realms are where our current understanding truly frays. They are the here-be dragons on the map of cosmological thought. They are often not well-formed theories, but rather imaginative explorations of the limits of possibility. However, even such far-flung ideas can sometimes inspire new avenues of more rigorous research or highlight hidden assumptions in our current models. As you drift in this sea of speculation, allow your mind to simply wonder at the sheer audacity of these concepts, the human capacity to imagine realities so profoundly different from our own, even if they remain firmly in the realm of what-if rather than established science. Our long, gentle journey through the myriad possibilities of the multiverse is now drawing to a close. We've explored universes born from the endless blossoms of cosmic inflation, realities branching off with every quantum tick, dimensions beyond our ken predicted by string theory, and cosmic cycles of eternal rebirth. We've pondered realities that might be pure mathematics, elaborate simulations, or even just distant, repeating patches of an infinitely vast space. We've touched upon the deep philosophical questions these ideas raise about fine-tuning, our own existence, and the very nature of reality and knowledge. And as we've just considered, the challenge of ever truly knowing whether these other universes exist, given their likely causal disconnection from our own, is a profound one. So, what are we to make of all this as we drift towards sleep? The concept of a multiverse, in its many forms, undeniably stretches the human imagination to its absolute limits. It forces us to confront the possibility that our entire observable universe, with all its galaxies, stars and planets, with all its history and all its future, might be an infinitesimally small part of a much grander, perhaps infinitely more complex, cosmic tapestry. This can be both a humbling and an exhilarating thought. Humbling because it relativizes our own cosmic significance. If there are countless other universes, perhaps with their own forms of life, or even consciousness, then our own existence, our own world, is not necessarily unique or central in any cosmic sense. We are but one variation among many, one possible outcome in a vast lottery of cosmic creation. This can be a powerful antidote to any lingering anthropocentric biases, reminding us that the universe, or multiverse, does not revolve around us. Exhilarating, because it opens up an almost boundless space for wonder and intellectual exploration. The idea that the laws of physics, the number of dimensions, the very nature of matter and energy could be different in other universes is a playground for the imagination. It suggests that reality itself might be far more diverse, far more creative and far stranger than our limited experience within this single universe can reveal. It hints at a meta-reality with principles so deep that they can give rise to such an astonishing variety of cosmic expressions. The philosophical implications are vast. If there are infinite versions of you in a quilted multiverse or a many-world scenario, what does this mean for your identity, your free will, your moral responsibility? If all mathematically possible universes exist, what does that say about the relationship between mind and mathematics, between the abstract and the concrete? If our universe is fine-tuned for life because it's just one, successful, member of a vast anthropic ensemble, does that diminish the sense of wonder at our existence, or does it place it within a grander statistical context? These are not questions with easy answers, and they are likely to be debated by philosophers and scientists for as long as we ponder our place in the cosmos. For many scientists, the multiverse is not just a wild speculation, but a logical if unproven consequence of our current best theories when pushed to their extremes. Theories like inflation, quantum mechanics, and string theory. If these theories are on the right track in describing our universe, and if they robustly predict the existence of other universes as a natural outcome, then the multiverse becomes a serious theoretical possibility, even if direct observation remains elusive. The challenge then becomes to refine these theories, to look for subtle indirect clues, or to understand if there are fundamental principles that might limit the extravagance of the multiverse, or select for certain types of universes. As you let these final thoughts wash over you, don't feel the need to arrive at any firm conclusions about whether the multiverse is real or not. The beauty of these ideas, especially as a companion to sleep, lies in their ability to expand our sense of perspective, to take us beyond the everyday and into the realm of the truly profound. They remind us that our current understanding of reality is undoubtedly incomplete, that there are vast oceans of mystery still to explore. The very fact that the human mind can conceive of such possibilities, can use mathematics and logic to explore realms so far beyond our direct experience, is itself a source of wonder. Let the idea of countless other worlds, each with its own story, its own secrets, be a gentle backdrop to your own drift into slumber, a reminder of the infinite potential and the enduring mystery that surrounds us. Word count 1098. And so, our extensive exploration of the myriad forms a multiverse might take, from the bubbling froth of eternal inflation to the serene abstract landscapes of mathematical existence, gently comes to a close. We've allowed our minds to drift across cosmic scales and through dimensions unseen, contemplating the possibility that our familiar universe is but one thread in an infinitely richer, unimaginably vast tapestry of realities. We've touched upon how quantum mechanics might branch our world into countless parallel streams, how string theory might weave together universes with different physical laws from the vibrations of tiny strings in curled-up dimensions, and how even the sheer infinitude of space might ensure that somewhere far beyond our horizon, exact copies of our world and ourselves repeat. The thought of black holes birthing new universes, or our own reality being a sophisticated simulation or a mere hologram projected from a distant boundary, can feel both exhilarating and profoundly unsettling. These are not concepts meant for immediate, concrete comprehension, especially as the gentle pull of sleep grows stronger. Instead, they are offerings to the curious mind, whispers of the immense unknown that lies beyond our current understanding. If these ideas have sparked a sense of wonder, a feeling of smallness in the face of cosmic grandeur, or simply a quiet contemplation of what is versus what could be, then they have served their purpose. There is a unique tranquility in acknowledging the profound mysteries that underpin existence, a peaceful surrender to the idea that the universe, or the multiverse, is far stranger and more magnificent than we can perhaps ever fully grasp. Let these mind-expanding thoughts now soften, dissolve, and merge with the approaching calm of deep rest. The other worlds, whether real or imagined, will wait. Your own world, for now, is calling you to the quiet sanctuary of sleep. Sweet dreams.